Hello guys, in today's video we're going to do the Hahn-Banach theorem for real vector spaces. Starting with the statement of the proof, what does the theorem says essentially? So let X be a real vector space and P from X to R be a sublinear mapping. We discussed the concept of a sublinear mapping in the previous video, the road to Hahn-Banach theorem. But I would again tell you what the definition of sublinear mapping is. So sublinear mapping is a functional which satisfies these two properties. You can go to the previous video to check it again. So X be a real vector space and P be a sublinear mapping, and X naught be a proper subspace of X. And we have this F naught defined from X naught to the real numbers. It's a linear mapping and it has this property. So this is given. Now what we need to prove is that this part, that there exists a F from whole of X to R with the property that F restricted to X naught is equals to F naught, and it satisfies this sublinear property that in the same way F naught X naught was less than P of X naught, we want F of X to be less than P of X for every value of X belonging to capital X. Now let us look at this proof piece by piece. It's a very complicated proof which involves layers and layers of abstraction, but that's why I have broken it down into small pieces which can be easily seen. So let's look at this. Now let M be a family of pairs of y's and f of y's with the property. So we are constructing a family of pairs. You see, how are we constructing this family? We are constructing it in this way, that y is a subspace of x and x naught is a subspace of y. So x naught was the space on which the functional which was given to me was defined, and now I take a subspace capital Y such that x naught is again a subset of capital Y and Y is a subspace of X, so x naught is also a subspace of capital Y. And again I have f of y. F of y is a linear mapping from capital Y to R with these two properties, that f of y restricted to x naught is equals to f naught and fyx is less than or equals to p of x. So this is by construction. I'm constructing my family in this way. I'm constructing a family in this way such that property number 1 is satisfied and property number 2 is satisfied. And now we are saying that M is not empty because x naught f naught is a member of my M. And the next thing that I want to show, that these subsets and subspaces are entailed within each other. What I mean to say it as this pair y1 fy1 is less than or equal to y2 fy2 if and only if y1 is a subset of y2 and fy2 restricted to y1 is equals to f of y1. So this is how I define my partial ordering. I am saying that this was my partial ordering. This partial ordering holds if and only if these two conditions are satisfied, that y1 is a subset of y2 and fy2 restricted to y1 is equals to fy1. Now I have a partial ordering on my family of pairs. So one thing I would like to tell you about the steps we have done till now is that I would like to extend x naught to the whole of x. So as an intermediate step, I look at all the y's to which I can extend. So this is the reason behind constructing this family capital M. And now suppose there is a y and I look at all possible choices of that y that I could extend to. So one other justification for constructing this y is that I don't know if there is a y or if there is not a y, But at least I know that this family is not empty and that relation is satisfied for x naught, f naught. And I am constructing this y, this capital Y, in the hope that there exists small y's to which I can extend. So as we saw in, if you would like to see that the last proof that we did with the road to Hahn Banach, we did that there is a proper x naught. We did that X was a real vector space, there was a sublinear mapping, and X naught was a proper subspace. And then we extended it just by 1x, the span of this X, in the last proof. So in the same way, I'm saying that, okay, let us take all those Y's to which I can extend and say that those small Y's belong to my capital Y. So that's why I had this initial idea of extending my x naught to capital Y. And I say, okay, now since capital M is a partial ordering, I can define a chain in this. So if I take any chain, capital N, to be yi fi in my partial ordering capital M, then it follows that capital Y is the union of all yi's. And f of y, f of capital Y, x is equals to f of ix for all those x belongs to yi. The same point as I said. So we saw in the previous proof, the road to Hahn Banach, that I was extending my x naught to the span of x. So I take all those individual x and I put it in y's. And then step by step, I am extending my operator or my functional from x naught to x naught plus span of x. So that is my intuition behind doing that step. And we know that this partial ordering has an upper bound, that is for all yi's fi's we either have this condition or this condition, and it follows that y is a subspace of x and f is well defined and linear. So a quick recap, what did we do till now? All that we did till now is, in this space, we defined a partial ordering. So let me write it down. So this is define partial ordering on M. I took a family of pairs and then I defined a partial ordering on them. And now I said that within that partial ordering exists a chain such that this chain, capital N, has a maximal element. So within my partial ordering, exists a chain with a maximal element. So I took any chain, see this N is any chain, and that capital M could have an infinite number of chains, and that chain that I took has a maximal element given by this y, fy is the maximal element of my chain. Now let's take a look back into the Zorn's lemma that we did before. What did it tell us? So what the Zorn's lemma said was, let X be a partially ordered set with the property that each chain X has an upper bound. Yes, we have this in our construction. It follows that X has a maximal element. So you can think of it in this way, that I have a partial ordering and I have different chains in it. Let me draw the different chains with different elements with different colors. So I have a partial ordering and I have different chains in it. I have different chains in it. And now what the Zorn's lemma says is that there exists a maximal element. So there exists an element such that it is the maximal of every element in this chain. And that's it, kaboom. Now I say that I have these chains defined on my partial ordering, and every chain has an upper bound. So X itself has an upper bound. So in the same way, the capital M has an upper bound, and now we show that that upper bound indeed is capital X and F. This capital X and F as a pair is the upper bound of my partial ordering on the family of pairs. So according to Zorn's lemma, M has a maximal element CFC, and we show that C is not equals to 0 since capital M is not empty. And now we show by contradiction that suppose C is not equals to all of X, then using the previous proposition that we studied in the road to Hahn-Banach, it's very important for you to go back and understand that last proposition that we studied in the road to Hahn-Banach, because that helps us with the last part of the proof. So in the road to Hahn-Banach, I had a space X0, which was a subspace of capital X, and I extended it by a span of one element. So in the same way, I say that let Z not be equal to X, then using the previous proposition, we can extend FC to a linear mapping with this property, and it follows that. So now if I extend to the linear mapping, it follows that CFC is less than or equal to Z direct sum span of C and F. And this contradicts the maximality of C, FC, because as we say that Zorn's lemma said that M has a maximal element this, and when we say that this Z is not equals to all of X, then using the previous proposition we can further extend this Z, but this violates the condition that this was my maximal element, so my assumption was wrong and Z is indeed all of X. And in this way, I prove my Hahn-Banach theorem for real vector spaces. A final quick recap of the processes that were involved in this proof. So in this part, I defined M, which is a family of pairs, and I defined a partial ordering on M. In this part, I took any chain in this partial ordering, and the construction of my partial ordering was done in such a way that each chain has an upper bound, and in my chain N, the upper bound was given by this pair, capital Y F of Y. Now I invoke the Zorn's lemma. I say that okay, I had a partial ordering and I had chain defined on it such that every chain has a maximal element. Therefore, M itself has a maximal element. I call this maximal element ZFC, and then I prove by contradiction that Z is indeed my capital X, so that my functional can be extended from X0 to capital X, and it satisfies this property. See you in the next proof.